Hey guys, tonight we're diving into the quantum realm, that strange foggy basement of reality where particles forget how to behave like anything you've ever seen. Picture this. You're standing in a dark laboratory at 3 a.m, staring at a metal plate with two narrow slits carved into it. Behind the plate, a screen glows faintly, waiting. You fire a single electron, one tiny speck of matter so small it makes a grain of sand look like a planet, toward those slits. Common sense whispers that the electron will pass through one slit or the other, then hit the screen behind it, leaving a single dot. But common sense, as you're about to discover, doesn't work down here in the quantum basement. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment with where you're watching from and what time it is for you right now. I love seeing the Global Insomnia Club check in. Some of you are having morning coffee while I'm putting others to sleep. Beautiful chaos. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You fire that electron. It travels through the darkness, a lonely traveller on a journey measured in billionths of meters, and then something impossible happens. When you look at the screen behind the slits, you don't see a single dot. You see an interference pattern, a series of light and dark bands like ripples on a pond where two stones have been dropped. But here's the thing, you only fired one electron. One. How does a single particle create a pattern that requires waves interfering with each other? It's as if the electron somehow went through both slits simultaneously, split itself into a ghost of possibilities, interfered with its own quantum shadow, and then reassembled on the other side. Your brain, evolved to track predators on the savannah and find ripe fruit, absolutely hates this. It violates everything you know about how objects move through space. A baseball doesn't go through both the left and right side of a doorway at once. Your cat doesn't simultaneously use both the pet door and the window, but electrons, photons, all the microscopic citizens of the quantum realm. They apparently didn't get the memo about picking one path and sticking with it. Now you decide to investigate. You set up a detector at one of the slits, just a tiny observer, quietly watching to see which slit the electron actually uses. You fire another electron, the detector clicks. Aha, you think. Got you. You went through the left slit. You look at the screen. The interference pattern has vanished. Now you just see two bright patches behind the slits. Exactly what you'd expect if electrons were normal, well-behaved particles choosing one slit or the other. The act of watching, of measuring which path the electron took, has fundamentally changed the outcome. The universe, it seems, performs differently when it knows you're paying attention. Creepy, right? Like reality itself is camera shy. This is the famous double-slit experiment, and it's been driving physicists to existential coffee breaks since the 1920s. It reveals the first great truth of quantum mechanics. At the smallest scales, matter doesn't behave like matter. It doesn't behave like energy either. It behaves like both, like neither, like some shimmering thing that refuses to be pinned down until you force it to choose. And even then, it only chooses because you made it choose. Left alone, unwatched, a quantum particle exists in what physicists call a superposition, a state where it takes all possible paths, explores all possible positions, samples all possible versions of its own future simultaneously. Your classical intuition is screaming right now. That's okay. Let it scream. We're only in section 1, and it's going to have many more opportunities for existential panic before we're through. The quantum realm operates on rules that seem designed by a cosmic prankster with a philosophy degree. Down here, particles tunnel through walls. Pairs of particles share information across cosmic distances instantaneously. Empty space seethes with energy. Cats can be both alive and dead, and observation, the simple act of looking, becomes a fundamental force that shapes reality itself. Welcome to the basement, friend. It's weird down here, but you'll get used to the vertigo, or at least you'll learn to enjoy the falling sensation. Tonight, we're going to explore this quantum wonderland slowly, carefully, like tourists with a good flashlight and no particular place to be. We'll meet the particles that refuse to hold still. We'll encounter the physicists who first stumbled into this bizarre realm and couldn't quite believe what they were seeing. We'll explore entanglement, superposition, tunneling, and all the greatest hits of quantum weirdness. And we'll do it all at a pace designed for heavy eyelids and wandering thoughts, because the quantum realm, despite its strangeness, has a certain meditative quality. It asks you to let go, to accept mystery, to be comfortable with uncertainty, which, conveniently, is also excellent advice for falling asleep. So settle in, pull the blanket a little higher, let your breathing slow. We're about to spend the next few hours in a place where the impossible is routine, and reality waits for permission before solidifying. The quantum realm doesn't care if you understand it. It's been doing its probabilistic dance for billions of years without your approval, but maybe, just maybe, by the time your eyes finally close tonight, you'll have glimpsed something beautiful in the uncertainty, a universe far stranger and more wonderful than the one you thought you lived in. You're still in that laboratory, but now you're zooming in closer, watching a single electron prepare for its journey. It sits there, if sits is even the right word for something that doesn't really have a location until you check, like a guest at a party who hasn't decided whether to stay or leave. The electron is incredibly small. If you scaled an atom up to the size of a football stadium, the electron would be smaller than a grain of sand on the 50-yard line. And yet this microscopic speck is about to demonstrate something that will make you question whether particle and wave are even useful words anymore. Fire that electron toward the double slits again. No detectors this time, no watching. Just the electron, the slits, and the screen. As the electron travels, it stops being a definite point in space and becomes something else. A probability wave, a mathematical ghost that spreads out like ripples in a pond. This wave doesn't represent the electron's motion through water or air. It represents something far stranger, the electron's potential to be in multiple places simultaneously. The wave passes through both slits at once, because waves do that. Waves don't choose. They explore every available path, spreading their amplitude across space like gossip through a small town. The two parts of the wave, one through the left slit, one through the right, continue their journey toward the screen. Where the wave peaks meet other wave peaks, they add together, creating bright bands of high probability. Where peaks meet troughs, they cancel out, creating dark bands where the electron will never appear. This is interference, the signature behavior of waves. Ocean waves do it, sound waves do it, light waves do it, and apparently electrons, those tiny, solid, particle-like things, do it too. But here's where your intuition starts glitching like a corrupted video file. When the electron finally hits the screen, it arrives as a particle. One discrete impact, one tiny flash of light, not a spread-out wave, not a smeared probability, a definite localized click. The electron collapsed from being everywhere at once into being somewhere specific. It's as if the wave was just the electron's way of exploring its options, and the screen forced it to finally commit to a decision. Fire 1,000 electrons one at a time, and slowly the interference pattern emerges on the screen, those alternating bright and dark bands. Each electron went through both slits as a wave, interfered with itself, then arrived as a particle at a location determined by the wave's probability distribution. The electron is both particle and wave, or neither, depending on when you ask the question. Physicists call this wave-particle duality, which is really just a fancy way of saying we're as confused as you are, but we've given the confusion a professional name. This duality isn't unique to electrons. Photons, particles of light, do it too. In fact, every quantum object exhibits this schizophrenic behavior. Sometimes light acts like a wave spreading through space, diffracting around corners, creating those beautiful rainbow patterns in soap bubbles. Other times, light acts like a stream of particles, little packets of energy called photons that hit solar panels one discrete tick at a time. Einstein won his Nobel Prize not for relativity, but for explaining how light knocks electrons out of metal surfaces, the photoelectric effect, which only makes sense if light comes in particle-sized chunks. Meanwhile, Thomas Young's double-slit experiment with light, performed way back in 1801, proved conclusively that light was a wave. Both were right, both were also wrong in a sense. Light is whatever it needs to be for the situation at hand. You might be wondering, maybe things are weird at tiny scales, but surely this doesn't apply to real objects, right? Surely your coffee cup doesn't exist in multiple places until you look at it. And you'd be correct, sort of. The larger an object gets, the more its wave nature becomes practically undetectable. A baseball has a wavelength, technically, but that wavelength is so absurdly small that the ball behaves entirely like a classical particle. The quantum fuzziness is still there, mathematically speaking, but it's diluted across so many trillions of atoms that it averages out to normal, boring, predictable motion. But here's the delicious part. In 1999, physicists in Vienna managed to pass molecules through a double-slit setup and observe interference patterns. Not single atoms, full molecules made of 60 carbon atoms arranged in a soccer ball shape called buckyballs. These molecules, large enough to be visible under a good microscope, still behaved like waves when nobody was watching which slit they used. The quantum realm's borders extend further into our everyday world than you might think. Though I should mention, they still haven't managed this trick with anything much larger. Your car is safe from suddenly being in 2 parking spaces at once. Probably. The philosophical implications here are pretty wild if you let yourself think about them. That electron didn't secretly go through one slit while you weren't looking. It genuinely explored both possibilities simultaneously. The wave isn't an approximation or a convenient mathematical fiction. It's a real description of what the electron is doing, existing in a superposition of states, taking all paths available to it, living every possible version of its journey at once until something forces it to collapse into a single, definite history. Reality, at the quantum level, is fundamentally probabilistic. It's not that we lack information about where the electron is, it's that the electron itself doesn't have a definite location until measurement creates one. This makes the universe less like a clockwork machine, and more like an improvisational jazz performance, riffing on themes, exploring possibilities, and only solidifying into definite notes when someone's listening. You're reaching for that electron again, trying to pin it down, trying to know everything about it. Reasonable goal, right? If you can measure where something is and how fast it's moving, you should be able to predict its entire future. That's how physics worked for centuries. Newton's laws were beautifully deterministic. Give me the position and velocity of every object in the universe, and I'll tell you where everything will be 1,000 years from now. The cosmos was a predictable machine, ticking along like a grandfather clock. Then Werner Heisenberg showed up in 1927 and broke the clock. Heisenberg was in his mid-20s, working under Niels Bohr in Copenhagen, and he realised something disturbing while trying to mathematically describe quantum systems. The more precisely you measure a particle's position, the less precisely you can know its momentum. Not because your instruments are clumsy, not because you need better technology, but because the universe itself doesn't allow both pieces of information to exist simultaneously with perfect precision. It's a fundamental limit built into the fabric of reality, like a cosmic rule that says you can't have it all. Imagine you're trying to photograph a hummingbird in flight. To capture its exact position, you need a very fast shutter speed, freeze that moment perfectly. But with a fast shutter, you can't see the motion blur that would tell you how quickly it's moving. To capture its velocity, you need a longer exposure that shows the blur of motion, but then you lose the precise information about where it is at any given instant. Now imagine this isn't a limitation of your camera, but a limitation of the hummingbird itself, that the bird literally doesn't have both a definite position and a definite velocity simultaneously. That's the quantum world. The math is elegant and cruel. Heisenberg's uncertainty principle states that the product of the uncertainties in position and momentum must be greater than or equal to a tiny number called Planck's constant divided by 2. In practical terms, squeeze down the uncertainty in position, and the uncertainty in momentum balloons outward. Pin down the momentum precisely, and the position becomes a fuzzy cloud of possibilities. The universe enforces a minimum amount of ignorance, a mandatory zone of unknowing that you cannot overcome with better equipment or cleverer techniques. This isn't about measurement disturbing the particle, though that happens too. Shine light on an electron to see where it is, and the photon you use will bump the electron, changing its momentum. That's a practical problem, sure, but Heisenberg's principle goes deeper. Even before you measure anything, even when the particle is sitting alone in the dark, it doesn't possess both definite position and definite momentum. Those properties exist in a relationship of mutual exclusivity, like two people who refuse to be at the same party. The particle exists in a state of irreducible fuzziness, and the universe simply won't let you eliminate that fuzziness completely. There's a beautiful symmetry to this uncertainty. Position and momentum are what physicists call conjugate variables. Pairs of properties connected through Fourier transforms, the same mathematical structures that relate the time domain and frequency domain representations of sound waves. A pure musical tone has a definite frequency, but exists across all time. A sharp click in time has no definite frequency. It contains all frequencies simultaneously. You can have one or the other, but not both with perfect precision. Electrons follow the same rule. They can be sharp in position, but smeared in momentum, or vice versa, but never perfectly defined in both simultaneously. Einstein hated this. He spent years trying to find loopholes, thought experiments that would demonstrate how quantum mechanics must be incomplete. God does not play dice with the universe, he famously complained, to which Bohr supposedly replied, Einstein, stop telling God what to do. The debate wasn't really about dice or randomness. It was about whether reality has definite properties before we measure them. Einstein believed particles had real positions and momentums that we simply didn't know yet. Heisenberg and Bohr insisted that particles don't have those properties until measurement forces them into existence. The universe, they argued, is fundamentally indeterminate at its core. Decades of experiments have sided with Bohr and Heisenberg. The uncertainty isn't a gap in our knowledge. It's a gap in what's knowable, because it's a gap in what exists. An unmeasured electron doesn't have a hidden position that you're merely ignorant of. It has a spread of possible positions, a probability distribution, and nothing more definite than that. The electron is genuinely uncertain about its own properties, if you can even use the word uncertain for something that isn't secretly certain, but just unknown to you. You can apply this principle to other conjugate pairs too. Energy and time are conjugate variables. There's an uncertainty relation between them. The more precisely you try to measure when a quantum event happens, the fuzzier its energy becomes. This has real consequences. Virtual particles can briefly violate energy conservation by borrowing energy from the vacuum, as long as they pay it back quickly enough that the energy-time uncertainty principle isn't violated. The universe allows temporary rule breaking in the gaps between what's precisely knowable. The philosophical weight of this is staggering if you unpack it slowly. Determinism, the idea that the future is already decided by the present, dies here in the quantum realm. You cannot predict an electron's future perfectly because the electron's present isn't perfectly defined. The universe protects its quantum citizens with a veil of probability that cannot be lifted. And this isn't some esoteric effect that only matters in particle accelerators. This uncertainty is why atoms are stable, why electrons don't spiral into the nucleus, why chemistry works the way it does. The uncertainty principle keeps matter from collapsing into a point. It gives atoms their size, their structure, their very existence. You're held together right now by Heisenberg's fundamental limit on knowability. You're getting comfortable with uncertainty now, or at least you're learning to coexist with it, which is good because things are about to get weirder. Erwin Schrödinger enters the scene in 1935, looking slightly annoyed. He's been watching this whole quantum mechanics project develop, contributing to it himself with his famous wave equation, but he's growing increasingly uncomfortable with what it all means. So he decides to illustrate his concerns with a thought experiment involving a cat, a box, and a genuinely disturbing amount of casual cruelty toward hypothetical pets. Here's the setup. You take a cat and place it in a sealed box. Inside the box, you also place a tiny bit of radioactive material, a Geiger counter, a hammer, and a flask of poison. The radioactive material has exactly a 50% chance of decaying within 1 hour. If it decays, the Geiger counter detects it, triggers the hammer, which smashes the flask, releasing the poison, killing the cat. If the material doesn't decay, the cat lives. Simple enough, dark, but simple. You close the box and wait 1 hour. Now, according to quantum mechanics, that radioactive atom exists in a superposition of states, both decayed and not decayed simultaneously, until someone observes it. The atom is smeared across both possibilities, like quantum butter on the toast of reality. But if the atom is in superposition, and the Geiger counter's state depends on the atom, then the Geiger counter must also be in superposition, both triggered and not triggered, which means the hammer is both fallen and not fallen, which means the flask is both broken and intact, which means if you follow this chain of quantum logic to its absurd conclusion, the cat is both alive and dead at the same time. Not either alive or dead, but you don't know which. Actually both, simultaneously. a furry superposition of life and death, existing in some bizarre limbo state that defies everything your brain understands about cats, or life, or death, or boxes. Schrödinger proposed this thought experiment not because he believed cats actually entered superposition states, but because he wanted to show how absurd it was to apply quantum rules to macroscopic objects. He was essentially saying, look, if we take this Copenhagen interpretation seriously, we get results that are obviously ridiculous. Therefore, something must be wrong with our understanding. The problem is, quantum mechanics didn't blink. The math worked perfectly. The predictions matched experiments flawlessly. The theory just shrugged and said, yeah, superposition cats, what about it? Physicists have been arguing about what this means ever since. Schrödinger's cat became less of an argument against quantum mechanics and more of an uncomfortable mascot for its philosophical problems. Let's dig into what superposition actually means, because it's slippery. When that radioactive atom is in superposition, it's not that it has secretly decayed or secretly not decayed and you simply don't know which. It genuinely hasn't decided yet. It exists as a mathematical combination of both states, described by a wave function that assigns amplitudes to each possibility. The atom is exploring both futures simultaneously, keeping its options open, refusing to commit until forced to by an observer. Think of it like a person standing at a fork in a road, but somehow walking down both paths at once, experiencing both journeys, until someone asks them which way they went and the answer crystallizes into a single definite history. But here's where it gets really mind-bending. What counts as an observer? Does the Geiger counter count? It's a machine, not a conscious being, but it's definitely measuring the atom's state. Does the cat count? Presumably the cat knows whether it's been poisoned or not. The cat is observing its own aliveness. So does the superposition collapse when the Geiger counter clicks? Or when the poison hits the cat's bloodstream? Or only when you open the box and look? Different interpretations of quantum mechanics give different answers to this question, and none of them are entirely satisfying. The Copenhagen interpretation, championed by Niels Bohr, says that the wave function collapses when a measurement occurs, but it's frustratingly vague about what constitutes a measurement. The whole system, atom, counter, hammer, flask, cat, remains in superposition until you open the box and observe it. Your observation causes the wave function to collapse into one definite state. This interpretation makes observation a fundamental force in the universe, which feels anthropocentric and weird. Do quantum systems wait around for humans to look at them before deciding what to be? Other physicists have proposed alternatives. Some say consciousness is required to collapse the wave function, which opens a whole can of philosophical worms about what consciousness is and whether cats have it. The cats definitely think they do. They're quite firm on this point. Others argue that the wave function never actually collapses. We'll get to that deliciously bizarre interpretation later, and that every possible outcome occurs in separate parallel universes. Still, others suggest that the environment itself acts as an observer through a process called decoherence, which we'll also explore in depth later. What Schrödinger's cat really demonstrates is the measurement problem, the bizarre fact that quantum systems seem to exist in superposition until observed, at which point they choose a definite state. This collapse of the wave function happens instantaneously and seems to violate the smooth, deterministic evolution that the Schrödinger equation predicts for unobserved systems. It's as if the universe operates under two completely different sets of rules: gradual, wave-like evolution when nobody's watching, and sudden, discontinuous collapse when someone is. The cat is fine, by the way. No actual cats were harmed in any physics thought experiments, though you do have to wonder what the cat thinks about all this philosophical fuss being made over its hypothetical demise. Probably it's more concerned with dinner, and whether that red dot on the wall is finally catchable this time. You've made it this far into the quantum realm without your brain completely melting, which is impressive. You've accepted wave-particle duality, uncertainty, and superposition. You're nodding along, thinking maybe you can handle this weirdness, and then quantum entanglement shows up, and suddenly everything you thought was strange looks quaint and reasonable by comparison. Entanglement is where quantum mechanics stops being merely counterintuitive and starts being actively confrontational toward your sense of reality. Here's how you create entangled particles. Take a single photon with enough energy and pass it through a special crystal. Under the right conditions, the photon splits into two lower energy photons that fly off in different directions. These two photons are now entangled, connected in a way that transcends normal spatial relationships. They share a quantum state. They're not just correlated like twins who happen to dress similarly. They're bound together in their very essence, part of a single quantum system that cannot be fully described by talking about each photon individually. Let's say these entangled photons have a property called spin. Quantum spin is a weird concept. It's not actually spinning in the classical sense, but it acts like angular momentum and can be measured along different axes. For our purposes, just think of it as a property that can be either up or down when you measure it. Before measurement, each photon exists in a superposition of both spin up and spin down. But here's the crucial part. The two photons are entangled in such a way that if you measure one and find it spin up, the other will instantly be spin down and vice versa. They're perfectly anti-correlated. Now, you let these photons fly apart. One travels to a detector in New York, the other travels to a detector in Los Angeles. 3,000 miles separate them, a distance that light takes about 16 milliseconds to cross. You measure the New York photon's spin. It comes up spin up. At that exact instant, not 16 milliseconds later, not after any signal could travel from New York to LA, the Los Angeles photon's spin becomes definite as spin down. Measure it a nanosecond later, and you'll find it spin down with absolute certainty. Your brain is probably screaming right now, how did the Los Angeles photon know what happened in New York? Did some signal travel between them? But no signal can travel faster than light. That's a bedrock principle of relativity. Einstein spent years proving that faster-than-light communication is impossible, that it would allow you to send messages backward in time and create all sorts of paradoxes. And yet here we have two particles, separated by a continent, coordinating their behavior instantaneously. The spooky part is that before you measured the New York photon, neither photon had a definite spin. They were both in superposition. The measurement in New York didn't just reveal information about the LA photon. It actually determined the LA photon's state, collapsing its wave function across 3,000 miles of space. The two photons remain a single quantum system, no matter how far apart they drift. Distance, that fundamental feature of reality that keeps your coffee separate from your neighbour's coffee, becomes meaningless for entangled particles. You can entangle more than two particles, by the way. Physicists have created entangled states involving hundreds of particles, all locked into a single quantum system where measuring one instantly affects all the others. There's no theoretical limit to how many particles can share an entangled state, or how far apart they can be. You could in principle entangle a particle on Earth with one on Mars, and they'd remain connected across millions of miles of empty space. The universe apparently doesn't care about your intuitions regarding locality. Here's what makes entanglement even stranger. You can't use it to send messages. This seems like a cruel joke. You have instantaneous correlation across arbitrary distances, but you can't exploit it for faster-than-light communication. Why not? Because the measurement results are random. When you measure the New York photon, you get spin up or spin down with equal probability. You can't force it to be spin up. You can't encode information in the result. The person in Los Angeles measuring their photon also sees random results. 50% up, 50% down. Only when you compare notes later, using conventional slower-than-light communication, do you discover that your results were perfectly correlated. It's like having two magic coins. You flip yours in New York and get heads. Instantly, your friend's coin in LA, when they flip it, will show tails. Every single time. Perfect anti-correlation across any distance. But since you can't control whether your coin shows heads or tails, you can't use this to send messages. You just end up with impressively coordinated random numbers. The universe gives you instantaneous connections, but carefully ensures you can't violate causality with them. It's maddeningly elegant. Entanglement isn't some theoretical curiosity either. It's been demonstrated in countless experiments. Photons, electrons, atoms, even small molecules have been entangled and measured. In 2022, the Nobel Prize in Physics went to 3 scientists who performed definitive experiments proving that entanglement is real and that the correlations can't be explained by hidden variables, secret information the particles carry with them. The universe really does maintain these impossible connections. Reality is non-local, in a way that should be science fiction, but is actually just science. What this means philosophically is profound. The universe isn't made of separate independent objects that interact through forces. At the quantum level, it's made of relationships, connections, correlations that transcend space. Those two photons aren't really two separate things. They're aspects of a single quantum entity that happens to be spread across 3,000 miles. Einstein was not having it. Not even a little bit. When he first encountered the implications of quantum entanglement in the mid-1920s, his reaction was essentially absolutely not. This is ridiculous, and I will spend the rest of my career proving it. Here was a man who had revolutionized physics twice, once with special relativity, again with general relativity, and now quantum mechanics was telling him that the universe operated on principles he found deeply, fundamentally wrong. So Einstein did what any stubborn genius would do. He started poking holes. The phrase spooky action at a distance comes from Einstein. He used it derisively, mockingly, the way you might say, yeah sure, and I'm the King of England. In German the phrase was spukhaft Fernwirkung, and it dripped with skepticism. Einstein believed that physical reality should be local, that objects are only directly influenced by their immediate surroundings, not by events happening far away. Entanglement violated this principle so flagrantly that Einstein concluded quantum mechanics must be incomplete. There had to be some deeper theory, some hidden variables that we couldn't yet measure, that would restore sensible locality to the universe. In 1935, Einstein teamed up with two colleagues, Boris Podolsky and Nathan Podolsky, to write a paper that would become famous as the EPR paradox. The argument went like this: assume quantum mechanics is correct and complete. Then you could create two entangled particles, separate them by a huge distance, and measure one particle to instantly determine properties of the other particle. But this would mean you're affecting the distant particle without touching it, without sending any signal, purely by making a measurement elsewhere. Einstein found this absurd. Either information was travelling faster than light, violating relativity, or the particles had definite properties all along that we simply didn't know about. Since faster-than-light signalling was unacceptable, Einstein concluded that quantum mechanics was missing something. Niels Bohr, the patriarch of quantum mechanics, read the EPR paper and basically rolled up his sleeves for a philosophical brawl. Bohr argued that you couldn't think of the two particles as separate, independent objects once they'd been entangled. They formed a single system, and it was meaningless to talk about one particle having definite properties independent of the other. The measurement apparatus, the particles, the observers, all of it formed one big interconnected quantum system, and trying to slice it up into separate pieces missed the whole point. Bohr was essentially saying that Einstein's intuitions about separability and locality, while reasonable at human scales, simply didn't apply in the quantum realm. The debates between Einstein and Bohr became legendary in physics. They'd argue during conferences, over dinner, during walks through parks. Einstein would propose thought experiments designed to show contradictions in quantum mechanics. Bohr would stay up all night working through the math, then present a rebuttal the next morning showing why Einstein's scenario either didn't work or actually confirmed quantum principles. This went on for years. It was like watching two heavyweight philosophers box in slow motion, each landing thoughtful punches backed by decades of experience. Einstein never accepted quantum mechanics as final. In letters to friends, he'd express his frustration. I, at any rate, am convinced that he does not throw dice, he wrote to Max Born, referring to God and the randomness inherent in quantum mechanics. Born wrote back suggesting that perhaps Einstein shouldn't presume to tell God how to run the universe. The disagreement was profound and personal. These weren't just abstract physics questions. They cut to the heart of what reality is, whether it's deterministic or probabilistic, whether the universe has definite properties before we measure them. What's fascinating is that both Einstein and Bohr were partly right. Einstein was correct that quantum mechanics allows for correlations across space that seem to violate locality. He was right to be disturbed by this. But he was wrong in thinking this meant the theory was incomplete. Bohr was right that quantum systems can't be understood as collections of separate objects with independent properties, but he struggled to articulate exactly what measurement meant and when wave function collapse occurred. The debate they started continues today in different forms, with different interpretations of quantum mechanics trying to resolve the tensions they identified. For decades, the Einstein-Bohr debate remained philosophical. There was no way to experimentally distinguish between Einstein's hidden variable theories and standard quantum mechanics. Both predicted the same results for any measurement you could actually perform. The question seemed destined to remain in the realm of interpretation, a matter of taste, of philosophical preference rather than experimental fact. Einstein died in 1955 still believing that quantum mechanics, for all its empirical success, was missing something fundamental. But Einstein, for once, was about to be proven definitively wrong. Well, not about to. It would take another decade after his death. But the pieces were falling into place for an experiment that would settle the question once and for all. A physicist named John Bell was about to show that Einstein's local hidden variable theories and standard quantum mechanics made subtly different predictions that could be tested. And when those tests were finally performed, reality would side with the spookiness. The universe, it turned out, really was as weird as Bohr claimed. Maybe weirder. You're staring at a wall, thick, solid, impenetrable. Billions of atoms locked together in a crystalline lattice, electrons bound tightly to their nuclei, forming an unbroken barrier. You throw a tennis ball at the wall, it bounces back, as tennis balls do, because walls are solid, and objects can't pass through solid matter. This is obvious. This is how reality works. Except in the quantum realm, particles look at walls and occasionally decide to just walk through them. No tunneling equipment, no secret doors. They simply appear on the other side, as if the wall was a suggestion rather than a rule. This is quantum tunneling, and it's one of the most practically important quantum effects, even though it violates every intuition you have about barriers and solidity. Here's what happens. Remember that particles aren't really particles, but probability waves. That wave function describing an electron's position doesn't end abruptly at a barrier. Instead, it decays exponentially as it penetrates into the forbidden region. Most of the wave is reflected, yes, but a tiny portion of it extends through the barrier and emerges on the other side. If the barrier is thin enough, there's a small but non-zero probability that the electron will be found on the far side, having passed through solid matter without ever occupying the space inside it. Let's slow this down because it's beautifully weird. You have an electron approaching a barrier, maybe a thin insulating layer in a microchip. Classically, if the electron doesn't have enough energy to climb over the barrier, it should bounce back every single time. Energy conservation forbids it from crossing. But quantum mechanically, the electron's wave function doesn't know about forbidden. The wave penetrates into the barrier, dying off exponentially with distance, but maintaining a small amplitude. On the far side of the barrier, the wave function has a tiny value, and since the wave function square gives the probability of finding the electron there, there's a small chance the electron will tunnel through. The probability depends on the barrier's height and width. Thick barriers are exponentially harder to tunnel through. The wave function decays too much before reaching the other side. High barriers are also harder to penetrate, but make the barrier thin enough or low enough, and tunneling becomes not just possible but probable. In fact, tunneling happens constantly in the quantum world. It's not some rare exotic phenomenon. It's routine, mundane, essential to how matter behaves at small scales. The sun is powered by quantum tunneling. Yes, really. Nuclear fusion in the sun's core requires hydrogen nuclei to overcome their electromagnetic repulsion and get close enough for the strong nuclear force to bind them together. But at the temperatures in the sun's core, hydrogen nuclei don't have nearly enough energy to classically overcome that repulsion barrier. They should bounce off each other forever, and the sun should be cold and dark. Instead, the hydrogen nuclei tunnel through the electromagnetic barrier, appearing on the far side where the strong force can grab them, fusing them into helium and releasing energy. The sun shines because of quantum tunneling. You exist because particles can do the impossible. Radioactive decay also depends on tunneling. An alpha particle, 2 protons and 2 neutrons bound together, sits inside a heavy nucleus, trapped by the strong nuclear force. Classically, it doesn't have enough energy to escape, but quantum mechanically, there's a small probability it will tunnel through the nuclear barrier and escape. Wait long enough, and that improbable event becomes inevitable. This is why radioactive materials decay. The alpha particles aren't gaining energy from somewhere. They're simply tunneling out, one by one, at rates determined by the barrier height and width. Half-lives, those characteristic decay times for radioactive isotopes, are essentially measures of tunneling probability. John Bell was working at CERN in 1964, probably eating a sandwich or staring at equations on a blackboard, when he stumbled onto something that would fundamentally change how we understand reality. He'd been thinking about the Einstein-Bohr debate, turning it over in his mind like a Rubik's Cube, and he realised something nobody had noticed before. Einstein's local hidden variable theories and standard quantum mechanics didn't just disagree philosophically, they made slightly different numerical predictions that could be tested experimentally. The question could be dragged out of philosophy departments and into laboratories. Bell's idea was mathematically elegant. He considered pairs of entangled particles flying off to distant detectors, just like we discussed earlier. Each detector can be oriented to measure the particle's spin along different axes, up, down, left, right, diagonal, whatever. If Einstein was right and particles had definite properties all along, hidden from us but real, then there should be limits on how strongly the measurement results could be correlated. Bell derived an inequality, a mathematical relationship that any local hidden variable theory must satisfy. It's called Bell's inequality, and it essentially sets an upper bound on how correlated the particles can be if they're carrying hidden information with them. The beautiful, devastating punchline: quantum mechanics predicts correlations that violate Bell's inequality. The predictions of quantum mechanics exceed the limits that any local realistic theory can achieve. If you measure entangled particles at specific angle combinations, quantum mechanics says you'll see correlations stronger than Einstein's framework allows. Bell had found the smoking gun, the experimental signature that could distinguish between spooky action at a distance and hidden variables. Reality had been cornered into giving a definite answer. Now, deriving an inequality is one thing. Actually testing it in a laboratory is another. You need to create perfectly entangled particle pairs, send them to detectors far enough apart that no signal could travel between them during measurement, orient the detectors at precise angles, and repeat the experiment thousands of times to build up statistics. The technical challenges were enormous, but physicists love nothing more than settling a decades-old debate with actual data, so they got to work. The first major experimental test came in 1972, performed by Stuart Friedman and John Clauser at Berkeley. They used entangled photons and measured correlations that violated Bell's inequality. Einstein's local hidden variables lost the first round, but the experiment had loopholes, ways that a determined skeptic could argue the results didn't definitively rule out local realism. Maybe the detectors were somehow communicating with each other. Maybe there was a selection bias in which photons got detected. The physics community needed cleaner experiments. Over the next decades, researchers systematically closed the loopholes. Alain Aspect performed beautiful experiments in France in the early 1980s, switching detector orientation so rapidly that no light-speed signal could coordinate the results. Anton Zeilinger's group in Austria pushed the distances between detectors to hundreds of meters, then kilometers. In 2015, multiple groups around the world performed loophole-free Bell tests, experiments so carefully designed that every conceivable classical explanation could be ruled out. The results were unambiguous, consistent, and undeniable. Bell's inequality is violated. Quantum mechanics is correct. Einstein's intuition about locality was wrong. This isn't just some esoteric detail that only matters to philosophers. What Bell proved, and what experiments confirmed, is that the universe is fundamentally non-local. Objects are not isolated entities with independent properties. Measuring a particle here can instantaneously affect the state of a particle over there, with no signal, no mechanism, no intermediary carrying the influence. The universe maintains correlations across space that simply cannot be explained by any local theory. Entanglement is real, irreducible, and deeply woven into the fabric of reality. The philosophical implications are staggering. You have to give up either locality or realism, the assumption that objects have definite properties independent of measurement. Most physicists have chosen to abandon realism, accepting that quantum systems genuinely don't have definite properties until measured. But that means reality itself is contextual, that measurement doesn't reveal pre-existing facts but actually participates in creating them. The universe is not a collection of objects with definite states. It's a network of relationships and potentialities that crystallize into actuality only when observed. Some physicists try to salvage realism by abandoning locality instead, accepting faster than light influences, But this creates its own problems, including potential conflicts with relativity. Other interpretations, which we'll explore later, attempt different compromises. But there's no way out that preserves both locality and realism. Bell proved it mathematically. Experiments confirmed it empirically. You can't have your classical cake and eat it too. In 2022, the Nobel Prize in Physics was awarded to John Clauser, Alain Aspect, and Anton Zeilinger for their experimental work testing Bell's inequalities. The Nobel Committee was essentially saying, this is one of the most important results in all of physics, a definitive answer to a question about the nature of reality itself. Einstein, brilliant as he was, had the wrong intuition. The universe operates on principles stranger than he could accept. Bohr, for all his sometimes murky philosophical pronouncements, had grasped something profoundly true about quantum mechanics. Bell's theorem closes one door and opens another. It tells us what the universe is not, locally realistic, but it leaves open the question of what the universe actually is. How do we make sense of non-locality? What mechanism, if any, connects entangled particles? And what does it mean that reality waits for observation before deciding what to be? Modern electronics couldn't exist without tunneling. Flash memory in your phone stores data by trapping electrons behind barriers that they can tunnel through when the right voltage is applied. Scanning tunneling microscopes, which can image individual atoms on surfaces, work by measuring the tunneling current between a sharp tip and the surface being studied. When the tip hovers just a few atoms above the surface, electrons tunnel across the gap, and the resulting current reveals the surface topology with atomic precision. These microscopes have taken photographs of individual atoms, made possible because electrons cheerfully ignore the vacuum gap that should be uncrossable. There's something philosophically provocative about tunneling beyond just its practical applications. It means that barriers aren't absolute. Given enough time, given the right circumstances, particles can end up in places they have no classical right to be. The universe is probabilistic all the way down, and impossibility is just another word for very low probability. Nothing is truly forbidden, only improbable. You might wonder, if particles can tunnel through barriers, why don't macroscopic objects do the same? Why can't you walk through walls? The answer, as usual, comes down to scale. Quantum tunneling probability decreases exponentially with both the size of the object and the thickness of the barrier. For something as massive as your hand and a barrier as thick as a wall, the probability is so astronomically small that it would take longer than the lifetime of the universe for it to happen once. You'd have better odds winning every lottery on Earth simultaneously for 1 trillion consecutive drawings. The math says it's technically possible, but the numbers say it will never ever happen. The quantum world allows miracles, but only very small ones. Still, there's something deeply satisfying about knowing that solidity is negotiable at quantum scales, that walls are permeable if you're small enough, that the impossible becomes merely improbable when you descend into the basement of reality where probability reigns supreme. You're floating in empty space, not the space between stars where at least there's the occasional atom of hydrogen drifting by, but truly empty space, a perfect vacuum, every particle removed, every atom evacuated, pure nothingness. The temperature is absolute zero, no energy, no matter, no motion, just void. You'd think this would be the quietest, most boring place in the universe, the ultimate null state where literally nothing happens. But you'd be wrong. The quantum vacuum is seething with activity, bubbling with particles that pop into existence and vanish again so quickly that they barely have time to introduce themselves. These are called virtual particles, and they're one of the strangest consequences of quantum mechanics. Remember Heisenberg's uncertainty principle? It applies to energy and time too. The more precisely you try to pin down when a quantum event occurs, the fuzzier its energy becomes. Flip this around. If an event happens quickly enough, energy conservation can be violated temporarily. The universe allows you to borrow energy from nowhere, as long as you pay it back fast enough that nobody can catch you in the act. The quantum vacuum exploits this loophole enthusiastically. Virtual particle pairs, usually an electron and its antimatter twin, a positron, spontaneously appear out of nothing, exist for a tiny fraction of a second, then annihilate each other and disappear. The amount of energy borrowed and the duration of the loan are inversely related through the uncertainty principle. High energy particles can exist for only brief moments. Lower energy particles can stick around slightly longer. But all of them are living on borrowed time, flickering ghosts that never quite become real, before vanishing back into the vacuum. This sounds like mathematical fiction, some artifact of the equations that doesn't correspond to anything physical. But virtual particles have measurable consequences. One of the most famous is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948. Take two uncharged metal plates and place them very close together in a vacuum. The virtual particles in the space between the plates are restricted. Only certain wavelengths can fit in the narrow gap, but outside the plates, all wavelengths of virtual particles can appear. This creates an imbalance. There are slightly more virtual particles pushing the plates together from the outside than pushing them apart from the inside. The result is a tiny but measurable attractive force between the plates, purely from the vacuum's quantum activity. When Casimir first predicted this, people thought it was absurd, a force generated by particles that don't really exist. But in 1997, Steve Lamoureux at the University of Washington measured the Casimir effect with exquisite precision, and it matched the predictions perfectly. The vacuum isn't empty. It has energy. It exerts pressure. Virtual particles aren't just mathematical conveniences. They have real measurable effects on the physical world. The quantum vacuum also affects atoms. An electron orbiting a nucleus isn't just responding to the nucleus's electric field. It's constantly being jostled by virtual photons popping in and out of existence. These interactions cause tiny shifts in the electron's energy levels, shifts that can be measured spectroscopically. This is called the Lamb shift, discovered by Willis Lamb in 1947, and it was one of the first pieces of evidence that the vacuum is actively doing something rather than passively being nothing. Quantum electrodynamics, the theory that describes how light and matter interact, accounts for these vacuum effects with stunning accuracy. The predictions match experiments to 1 part in a billion. Here's where things get cosmologically weird. If virtual particles are constantly appearing and disappearing everywhere in space, and each appearance represents a tiny amount of energy, then the vacuum itself has energy density. Empty space weighs something in a sense. You can calculate this vacuum energy density, and when you do naively using quantum field theory, you get an answer that's about 10 to the power of 120 times larger than what we observe cosmologically. This is called the vacuum catastrophe, or the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. The vacuum should have an enormous energy density that would cause the universe to expand so rapidly that atoms couldn't form. But it doesn't. Why the vacuum energy is so incredibly small, but not zero, is completely unclear. That non-zero vacuum energy might be what we call dark energy, the mysterious substance that's causing the universe's expansion to accelerate. About 70% of the universe's energy budget is dark energy, and our best guess is that it's the energy of the quantum vacuum. But why that energy has the specific tiny value it does remains profoundly mysterious. The quantum vacuum whispers something important about the universe, but we can't quite hear what it's saying. Virtual particles also play a crucial role near black holes. Stephen Hawking realized that when a virtual particle pair appears right at a black hole's event horizon, one particle can fall in while the other escapes. The escaping particle becomes real, carrying away energy. To an outside observer, the black hole appears to glow with thermal radiation, Hawking radiation. Black holes slowly evaporate, radiating away their mass particle by particle over incomprehensibly long timescales. The vacuum's quantum fluctuations ultimately doom even black holes to dissolution. The quantum vacuum is a reminder that nothingness is relative. Remove all matter, all radiation, cool everything to absolute zero, and you still have the quantum fields themselves, irreducible and active, generating fluctuations that occasionally bubble up into almost reality before subsiding again. The universe never truly rests. You're watching that superposition cat again, the one trapped in its box, simultaneously alive and dead. It's been sitting in superposition for a while now, patiently existing in multiple states at once, when suddenly a single air molecule from outside the box manages to leak through a microscopic crack. Just one molecule. It bounces into the box, ricochets off the Geiger counter, and escapes back outside. That's it. That's all it takes. The cat's superposition collapses, not because you opened the box and looked, not because some conscious observer made a measurement, but because the outside environment interacted with the quantum system, and when quantum systems interact with large, complex environments, their delicate superpositions get shredded into classical definiteness. This process is called decoherence, and it's the reason you don't see superpositions in everyday life. It's why your coffee cup isn't simultaneously on the table and on the floor. It's why you have a definite location instead of being smeared across multiple positions like a quantum ghost. Decoherence doesn't solve the measurement problem entirely. Philosophers still argue about what it all means, but it does explain why quantum weirdness stays hidden at macroscopic scales. The environment is constantly measuring everything, collapsing wave functions faster than you can blink. Here's how decoherence works in detail. A quantum system in superposition has phases. Different parts of its wave function have different complex values that can constructively or destructively interfere, creating those beautiful interference patterns we talked about earlier. But when the system interacts with its environment, colliding with air molecules, emitting photons, exchanging heat, information about the system's state leaks out into the environment. The environment becomes entangled with the system. And because the environment is enormous, containing billions upon billions of particles all doing their own chaotic dance, it's impossible to keep track of all those correlations. The phases that allowed interference patterns get randomized, washed out, destroyed. What remains looks like a classical mixture of definite states rather than a quantum superposition. The key insight is that decoherence doesn't make the wave function collapse into one state. The superposition technically still exists, but it's now entangled with an impossibly complex environment in a way that makes the different branches of the superposition unable to interfere with each other. For all practical purposes, the system has become classical. The quantum information hasn't disappeared, it's just been diluted across so many environmental degrees of freedom that it's unrecoverable. It's like trying to unmix cream from coffee. Technically possible in principle, practically impossible in reality. Decoherence is incredibly fast for macroscopic objects. That cat in the box, even if perfectly isolated, cosmic rays from space, neutrinos passing through, the faint glow of thermal radiation from the walls, all of these would cause decoherence in tiny fractions of a second. You can't maintain macroscopic superpositions because the environment won't let you. Everything is constantly being measured by everything else. The universe is one vast, interconnected web of quantum entanglement, and isolation is an illusion. Physicists can demonstrate decoherence experimentally by carefully tracking how quantum systems lose their quantum behavior as they interact with surroundings. They've watched molecules lose their ability to interfere with themselves as they collide with gas molecules. They've seen superconducting circuits decohere as they emit photons into their environment. The math matches observations beautifully. Decoherence explains why the quantum classical boundary exists without invoking consciousness or special measurement processes. The environment acts as an observer, collapsing superpositions through its relentless interactions. But, and this is important, decoherence doesn't solve the measurement problem completely. It explains why we don't see superpositions of macroscopic objects. It explains the practical emergence of classicality, but it doesn't explain why we experience one definite outcome when we make a measurement rather than experiencing a superposition of outcomes. When you measure that electron spin and find spin-up, decoherence explains why the measuring apparatus shows a definite reading rather than a superposition of readings. But it doesn't explain why you experience that reading instead of spin-down. Some interpretations of quantum mechanics say you do experience both, in different branches of reality. Others invoke additional collapse mechanisms. Decoherence alone leaves this question unanswered. What decoherence does provide is a bridge between quantum and classical worlds. It shows that you don't need to invoke consciousness or special measurement devices. The same physical processes that govern everything else in the universe are sufficient to make quantum systems behave classically when they interact with complex environments. This is deeply satisfying to physicists who dislike appeals to observers or minds as fundamental ingredients in physics. Decoherence makes the emergence of classicality a natural consequence of quantum mechanics itself, not something imposed from outside. The timescale for decoherence depends on how strongly the system couples to its environment. Isolated systems can maintain quantum coherence much longer. This is why quantum computers are so challenging to build. You need qubits that can stay in superposition long enough to perform computations, but but the environment is constantly trying to decohere them. Modern quantum computers operate at temperatures near absolute zero, shielded from electromagnetic radiation, isolated as thoroughly as human technology allows. Even then, coherence times are measured in milliseconds or microseconds before the environment wins and classical noise takes over. The fact that decoherence happens so quickly in warm, noisy environments like Earth's surface might explain why life evolved using classical rather than quantum information processing. Maintaining quantum states in biological systems is extraordinarily difficult, though we'll see later that nature has figured out some clever tricks in specific circumstances. You're sitting in front of a computer, not just any computer, a quantum computer, though it looks disappointingly mundane from the outside. Just a bunch of cryogenic equipment humming away, keeping the qubits inside colder than outer space. But inside that frigid chamber, something remarkable is happening. While your classical computer processes information bit by bit, evaluating one possibility at a time like a diligent bureaucrat working through a stack of forms, the quantum computer is exploring multiple possibilities simultaneously, exploiting that superposition weirdness to perform calculations that would take conventional computers longer than the age of the universe. Classical computers use bits, tiny switches that are either 0 or 1, off or on. String enough bits together and you can represent any number, any text, any image. Classical computation is deterministic and sequential. To check 1,000,000 possible solutions to a problem, a classical computer has to evaluate them one by one, methodically plodding through the space of possibilities. Quantum computers use qubits, quantum bits that can exist in superposition, being both 0 and 1 simultaneously. 2 qubits can be in a superposition of 4 states at once. 3 qubits, 8 states. 10 qubits, 1024 states. The number of simultaneous states grows exponentially with the number of qubits, and this exponential scaling is where quantum computers find their power. Here's a concrete example. Imagine you're trying to factor a huge number into its prime components. This is computationally hard for classical computers. The time required grows exponentially with the number of digits. It's so hard that modern encryption systems rely on this difficulty. Your credit card information is safe because nobody can quickly factor the large numbers used in RSA encryption. But in 1994, Peter Shor discovered a quantum algorithm that can factor numbers exponentially faster than any known classical algorithm. A quantum computer with enough qubits could break RSA encryption easily. This caused mild panic in cryptography circles and massive excitement in quantum computing research. How does Shor's algorithm work? By putting qubits into superposition, the quantum computer explores many possible factors simultaneously. Through clever manipulation using quantum gates, operations that rotate qubit states or entangle qubits together, the algorithm amplifies the probability of measuring the correct factors, while cancelling out wrong answers through quantum interference. It's like having many parallel universes working on the problem at once, with the incorrect solutions destructively interfering until only the right answer remains. When you finally measure the qubits, they collapse to the correct factors with high probability. But quantum computers aren't magical solution machines for every problem. They're only faster than classical computers for specific types of calculations that can exploit quantum parallelism and interference. Searching unsorted databases? Quantum computers provide a modest speed-up through Grover's algorithm. Simulating quantum systems? That's where quantum computers really shine, because they can naturally represent quantum states that would be impossibly complex to simulate classically. Optimization problems, machine learning, drug discovery all potentially benefit from quantum computation. But checking your email or watching videos, classical computers are perfectly fine and much easier to build. The main challenge in building quantum computers is decoherence, that environmental interference we discussed earlier. Qubits are incredibly fragile. They need to maintain superposition and entanglement long enough to complete calculations, but the environment is constantly trying to collapse them into definite classical states. Modern quantum computers use various physical systems as qubits: superconducting circuits, trapped ions, photons, nitrogen vacancy centers in diamonds, each with different coherence times and error rates. None of them are perfect. All of them require elaborate error correction schemes. Quantum error correction is beautifully ironic. You can't just copy a qubit to make backups. Quantum mechanics forbids cloning arbitrary quantum states, Instead, you encode one logical qubit across many physical qubits, spreading the quantum information so that errors can be detected and corrected without directly measuring the quantum state. It's like storing your data in a RAID array, but quantum. The catch is that error correction requires many physical qubits per logical qubit. Current estimates suggest hundreds or thousands of noisy physical qubits to make one reliable logical qubit. This is why today's quantum computers, with dozens or hundreds of qubits, are still in the noisy intermediate scale quantum (NISQ) era. They can perform interesting demonstrations, but aren't yet reliable enough for most practical applications. Still, progress is accelerating. In 2019, Google announced quantum supremacy. Their quantum computer performed a specific calculation in minutes that would take classical supercomputers thousands of years. IBM countered that with optimizations, classical computers could do it in days, not millennia. The debate continues, but the point stands. Quantum computers are beginning to enter territories where classical computers struggle. Companies and governments are investing billions into quantum computing research, betting that scalable, error-corrected quantum computers will eventually arrive. When they do, the implications extend beyond faster calculations. Quantum computers could discover new materials by simulating molecular interactions. They could optimize logistics networks, financial portfolios, and energy grids. They could break current encryption systems, forcing a migration to quantum-resistant cryptography. They might reveal new physics by simulating quantum field theories that are currently intractable. The quantum computer represents humanity's attempt to harness the weirdness of the quantum realm not just to understand nature, but to compute with it, to make the universe's fundamental strangeness work for us. And there's something philosophically satisfying about quantum computers. They force quantum mechanics out of laboratories and into practical technology. They're proof that superposition and entanglement aren't just theoretical curiosities, but resources that can be controlled, manipulated, and put to work. The quantum realm is becoming less of a mystery to peer at and more of a tool to wield. You're back in that laboratory, measuring that electron spin. You find its spin up. The measurement is complete, the wave function has collapsed, and you're confident about the result. But according to one interpretation of quantum mechanics, arguably the most audacious interpretation ever proposed, you didn't just measure the electron, you split the universe. Right now, in a parallel reality that's just as real as this one, another version of you measured that same electron and found it spin down. Both outcomes happened. Both versions of you exist. The wave function didn't collapse at all. It just branched, creating multiple parallel realities, each containing a slightly different version of you experiencing a different measurement result. This is the many worlds interpretation, proposed by Hugh Everett III in his doctoral thesis in 1957. Everett was frustrated with the Copenhagen interpretation's vagueness about measurement and wave function collapse. He looked at the Schrödinger equation, the fundamental equation governing quantum systems, and noticed something remarkable. The equation is completely deterministic and never includes any collapse mechanism. Wave functions evolve smoothly, continuously, predictably. The only place collapse appears is when physicists manually insert it to match experimental observations. Everett asked a simple question. What if collapse never happens? What if the Schrödinger equation is the complete story? If you take the Schrödinger equation seriously, without adding collapse, then superpositions never disappear. They just become more elaborate, spreading to include the measuring apparatus, the observer, the laboratory, eventually the entire universe. When you measure an electron in superposition, you become entangled with it. The universe splits into branches, one branch where you measured spin up and one where you measured spin down. Both branches are equally real. Both continue evolving according to quantum mechanics. From inside each branch, you experience a single definite outcome, but the universal wave function contains all outcomes simultaneously. Your brain is probably screaming about the extravagance of this idea. Every quantum measurement splits the universe. There must be trillions upon trillions of branches, a number growing exponentially with every quantum event everywhere in the cosmos. Every time a particle decays, every time a photon reflects or transmits through glass, every time anything quantum happens anywhere, the universe branches. Sounds insane, like someone took Occam's razor and decided to use it backwards, multiplying realities instead of minimizing assumptions. But here's the thing, many worlds doesn't add anything to the theory. It just refuses to add collapse, taking quantum mechanics at face value. The Copenhagen interpretation requires you to add collapse, an extra mechanism, unexplained and unmotivated by the equations, that somehow causes wave functions to discontinuously jump to definite states during measurement. It requires you to define what counts as a measurement, which turns out to be maddeningly difficult. Many worlds eliminates all that. Pure Schrödinger equation, no collapse, no special role for observers or measurements. Just deterministic quantum evolution producing an endlessly branching multiverse. In terms of theoretical economy, many worlds is actually simpler. It just costs you infinite copies of the universe. Each branch is completely isolated from the others. They can't communicate, they can't interfere. Once the universe splits, the branches are causally disconnected forever. This is why you can't perceive other branches or prove they exist directly. From inside one branch, you only experience that branch's definite outcomes. The other branches are as inaccessible as events outside your light cone. They're real, according to many worlds, but forever beyond your reach. So why do we experience probabilities if all outcomes occur? If every possibility happens in some branch, why does quantum mechanics predict that measuring spin-up has 50% probability rather than certainty? Many worlds answers this with the concept of measure over branches. The branches aren't equally weighted. The quantum amplitude squared, that probability from standard quantum mechanics, becomes a measure of how much world weight each branch carries. You're more likely to find yourself in high-amplitude branches because those branches contain more copies of you. It's an anthropic argument. You perceive probabilities because you're more likely to be one of the many copies in high-probability branches than one of the few copies in low-probability branches. Not everyone finds this satisfying. Critics argue that many worlds just relocates the mystery from why do we see definite outcomes to why do we experience subjective probabilities in a deterministic multiverse. They question whether it's scientific to postulate infinitely many unobservable universes. They worry about the philosophical implications. If every possible outcome occurs, does choice become meaningless? If there's a branch where you made every decision differently, does personal identity survive branching? Proponents counter that many worlds is the only interpretation that takes quantum mechanics seriously without adding mysterious extra mechanisms. Decoherence, which we discussed earlier, explains why branches become effectively isolated. Entanglement with the environment creates branches that can't interfere with each other. No collapse needed. The theory predicts exactly what we observe: apparent collapse, classical behavior at macroscopic scales, probabilistic outcomes, without requiring any mechanism beyond the Schrödinger equation. Philosophically, strange? Sure. But no stranger than insisting that conscious observation causes physical state reductions, or that particles lack properties until measured. Many worlds has gained popularity among physicists over recent decades, though it remains controversial. Part of its appeal is aesthetic. It's mathematically clean and conceptually coherent. Part is practical. It makes quantum computation easier to think about, with qubits exploring all computational paths simultaneously across branches. And part is simply the realization that all interpretations of quantum mechanics are weird. You can have collapse without mechanism, hidden variables with non-locality, pilot waves guiding particles, or infinite parallel universes. Pick your preferred flavor of strange. The many worlds interpretation suggests that reality is vastly larger and more diverse than we perceive. Every quantum possibility plays out somewhere in the multiverse. There are branches where you made different choices, pursued different careers, met different people. Branches where dinosaurs never went extinct, where Earth never formed, where fundamental constants differ slightly, creating unrecognizable physics. You're standing in a forest at dawn, watching light filter through the canopy. Photons from the sun are striking leaves, and inside those leaves, something remarkable is happening. Chlorophyll molecules are capturing photons and funneling their energy toward reaction centers with almost perfect efficiency. Around 95% of captured photons successfully contribute to photosynthesis. For decades, scientists assumed this process was purely classical chemistry. But in 2007, researchers discovered something unexpected. Plants appear to be using quantum coherence to optimize energy transfer. Biology, that messy, warm, wet domain that should destroy quantum effects instantly through decoherence, has apparently figured out how to exploit quantum mechanics. The discovery came from experiments on photosynthetic bacteria, measuring how energy moves through light harvesting complexes. Classical physics predicts energy should randomly hop from molecule to molecule, occasionally getting stuck or lost as heat. But the experiments showed energy travelling through multiple pathways simultaneously, interfering quantum mechanically to find the most efficient route. The energy exists in superposition across multiple molecules, exploring all possible paths at once, then converging on the reaction centre through constructive quantum interference. It's as if the plant is running a tiny quantum search algorithm inside every chloroplast, every moment the sun shines. How do biological systems maintain quantum coherence at room temperature, surrounded by noisy molecular vibrations that should destroy superpositions in femtoseconds? The answer appears to involve a delicate balance. The molecular vibrations don't just cause decoherence, they also help. At certain frequencies, environmental noise can actually protect quantum coherence through a phenomenon called environment-assisted quantum transport. The vibrations shake the system just right, preventing energy from getting trapped in local minima and helping it flow efficiently toward its destination. Nature evolved molecular structures that exploit rather than fight decoherence. It's breathtakingly clever. Birds might be doing something similar for navigation. Many migratory species can sense Earth's magnetic field, allowing them to navigate across continents with remarkable precision. But the magnetic field is extraordinarily weak, barely strong enough to deflect a compass needle, let alone influence biochemistry. How do birds detect it? One leading hypothesis involves quantum entanglement in the bird's eyes. Certain proteins in the retina contain pairs of electrons that become entangled when struck by blue light. Earth's magnetic field subtly affects how quickly these entangled pairs recombine, changing the chemical reaction rates in ways the bird's nervous system can detect. The bird literally sees magnetic fields as patterns overlaid on its visual perception, and this sense might depend on maintaining quantum entanglement in warm, wet biological tissue for tens of microseconds, an eternity by quantum decoherence standards. Evidence for this quantum compass comes from experiments showing that disrupting entanglement with radio waves interferes with birds' navigational abilities. The molecular details are still being worked out, and not everyone is convinced quantum effects are necessary to explain the observations. But the possibility that birds are flying quantum sensors, maintaining entangled states in their eyeballs while winging across oceans, is too fascinating not to investigate thoroughly. Quantum effects might even play a role in how you smell. The traditional theory of olfaction says your nose recognizes molecules by their shapes. Receptors bind to molecules that fit like keys in locks. But this theory struggles to explain why molecules with identical shapes but different isotopes can smell different. Heavy hydrogen, deuterium, forms slightly stronger bonds than normal hydrogen, making molecules vibrate at different frequencies. Some researchers propose that olfactory receptors detect these vibrational frequencies through quantum tunneling. An electron tunnels from one side of the receptor to the other, but only if the molecule's vibration has the right energy to accept the electron. Different vibrations create different tunneling probabilities, which your brain interprets as different smells. This is controversial, and classical theories might explain the observations, but experiments continue probing whether your ability to distinguish roses from violets relies on quantum mechanics. Then there's the question everyone wants to ask: does consciousness involve quantum effects? This idea gained popularity through books by Roger Penrose and Stuart Hameroff, who proposed that quantum computations occur in structures called microtubules inside neurons. They suggested consciousness arises from quantum superpositions collapsing in orchestrated ways throughout the brain. Most neuroscientists are deeply skeptical. The brain is warm, wet, and noisy, seemingly the worst possible environment for quantum coherence, and we have no evidence that classical neural computation is insufficient to explain cognition. Invoking quantum mechanics feels like invoking magic to explain something we don't understand yet, but some researchers take the possibility seriously. They point out that if photosynthesis and bird navigation can maintain quantum coherence in biological systems, maybe neurons can too. Anesthetics, which eliminate consciousness, also happen to disrupt quantum effects in microtubules. Correlation isn't causation, but it's suggestive. The question remains open, with most scientists betting that consciousness is classical, but a determined minority investigating quantum alternatives. Either way, the fact that we're even seriously asking whether your thoughts involve superposition and entanglement shows how far quantum biology has come. What's certain is that evolution has had billions of years to explore physical phenomena and exploit any advantage they provide. If quantum effects offer even slight improvements in efficiency or sensitivity, natural selection will find and optimize them. Life exists right at the boundary between quantum and classical regimes, sometimes crossing that boundary when the benefits outweigh the costs of maintaining fragile quantum states in hostile environments. The quantum realm isn't just an abstract physics playground, it's woven into the biological processes keeping you alive. You're back where we started, staring at that electron, preparing to measure its spin. But before you complete the measurement, you pause. This moment, this instant before the wave function collapses or branches, or does whatever it's supposed to do, contains the deepest mystery in all of quantum mechanics, the measurement problem. It's deceptively simple to state. Why does observation turn quantum possibilities into classical actualities? What exactly counts as a measurement, and what happens during that moment when superposition becomes definite reality? The Schrödinger equation describes how quantum systems evolve over time, and it's beautifully deterministic. Given a wave function at one moment, you can calculate its state at any future or past moment with perfect precision. The wave function spreads out, different parts interfere, probabilities shift, all smoothly, continuously, predictably. Nothing in the Schrödinger equation mentions collapse. Nothing suggests that wave functions should suddenly, discontinuously jump to definite states. Yet every time we measure something, that's exactly what appears to happen. The electron's wave function, spread across space in superposition, instantly localizes to a single position when detected. How? Why? The equation doesn't say. The Copenhagen interpretation, formulated primarily by Niels Bohr and Werner Heisenberg, addresses this by introducing the measurement postulate. When a measurement occurs, the wave function collapses to one of the possible eigenstates, with probability given by the amplitude squared. This postulate works perfectly for making predictions. It matches every experiment ever performed. But it leaves enormous questions unanswered. What constitutes a measurement? Does the measuring device have to be classical? Does it need to be macroscopic? Does consciousness need to be involved? The Copenhagen interpretation is frustratingly vague about these details, treating the quantum classical boundary as fundamental but undefined. Some interpretations, like the one proposed by Eugene Wigner, take consciousness seriously as the collapse mechanism. Only when a conscious observer becomes aware of the measurement result does the wave function collapse. This gives minds a fundamental role in physics, which feels deeply uncomfortable to most physicists. It also raises bizarre questions. Do bacteria collapse wave functions? Do insects? Where exactly does consciousness begin on the evolutionary scale? And what happened before conscious observers evolved? Did the entire universe exist in superposition for billions of years until the first brain appeared to collapse it? Other interpretations eliminate collapse entirely. The many worlds interpretation, which we explored earlier, says the wave function never collapses. It just branches, with observers splitting along with everything else. Pilot wave theories, championed by David Bohm, propose that particles have definite positions guided by a quantum wave, eliminating superposition at the cost of introducing non-local hidden variables. Objective collapse theories suggest that wave functions spontaneously collapse when systems reach certain sizes or masses, adding new physics beyond standard quantum mechanics to explain where quantum behavior ends and classical behavior begins. You're lying here now, eyes growing heavier, thoughts drifting between waking and sleep, and you're carrying with you this strange new knowledge about the quantum realm, that basement of reality where particles refuse to behave, where observation matters, where the impossible becomes merely improbable. And maybe you're wondering what it all means for you, for your life, for the world you navigate every day. Because quantum mechanics isn't just abstract physics happening in laboratories, it's the foundation of everything. Every atom in your body, every chemical reaction in your cells, every photon striking your retina right now, all of it operates on quantum principles, even if the weirdness averages out to classical predictability at human scales. The quantum world teaches you something profound about certainty. For For centuries, humanity believed the universe was fundamentally knowable, that with enough information and calculation, you could predict everything. Laplace imagined a demon with perfect knowledge that could foresee the entire future from the present state, but Heisenberg's uncertainty principle demolished that dream. The universe protects some information, enforces irreducible ignorance, maintains pockets of fundamental unpredictability that no technology or intelligence can overcome. There's something oddly liberating about this. The future isn't written. Determinism failed. Possibility remains genuine, not just an illusion born of ignorance. Quantum mechanics also changes how you think about separateness. You experience yourself as a distinct individual, separate from other people, from objects, from the environment. But entanglement suggests this separateness is superficial. At the quantum level, particles that have interacted remain connected across arbitrary distances, their states correlated in ways that transcend space. Every atom in your body has interacted with countless other atoms throughout cosmic history. In principle, you're quantumly entangled with the entire universe, a single, vast, interconnected system where boundaries between objects are conventional rather than fundamental. You're not a separate thing in the universe, you're a pattern of relationships within it. The measurement problem, that persistent mystery about how observation creates reality, hints at something strange about the relationship between mind and matter. Whether consciousness plays a special role or not, the act of measurement clearly matters in quantum mechanics. Reality at the smallest scale seems to wait for questions before providing answers. Properties don't pre-exist independently of observation. They emerge through the interaction of observer and observed. This doesn't mean you create reality through wishful thinking, but it does suggest that reality is more participatory than classical physics imagined. The universe isn't a pre-existing thing that you merely observe. It's something you're actively engaged with, moment by moment. Superposition, the ability of quantum systems to exist in multiple states simultaneously, offers a metaphor for human experience, if you're willing to stretch a bit. Before you make a decision, all possibilities exist in a kind of superposition in your mind. You're simultaneously the person who chooses this path and the person who chooses that path, until the moment of decision collapses those possibilities into a single actualized choice. The many worlds interpretation suggests those other versions of you really do exist in parallel branches, but even classically there's something profound about living in the space of possibility before choices crystallize into definite histories. Your life is a sequence of collapsed wave functions, each measurement determining who you become. Quantum tunneling reminds you that barriers aren't absolute. Particles can appear on the far side of walls they shouldn't be able to cross, not by breaking through, but by exploring probabilistic paths through the impossible. Sometimes in life, paths that seem completely closed turn out to have tiny quantum probabilities of opening. Most of the time, those probabilities are so small they might as well be zero. But occasionally, against astronomical odds, tunneling happens. The improbable becomes actual. Maybe there's wisdom in maintaining hope, even when barriers seem insurmountable, while also accepting that some walls really are too thick to tunnel through, no matter how long you wait. None of these solutions are fully satisfying. Each trades one set of philosophical difficulties for another. Many worlds requires accepting infinite unobservable realities. Pilot waves require accepting faster-than-light influences. Objective collapse theories require adding arbitrary parameters that haven't been observed experimentally. Copenhagen requires accepting fundamental vagueness about measurement. The measurement problem isn't a technical issue waiting for better experiments. It's a conceptual crisis about what quantum mechanics is telling us about reality. Here's what makes the measurement problem so stubborn. Quantum mechanics works. It's the most precisely tested theory in all of science. Predictions match observations to extraordinary accuracy. The theory is internally consistent, mathematically elegant, and phenomenally successful at describing nature. Yet we can't agree on what it means. We can calculate what will happen when we measure something, but we can't explain what happens during the measurement. It's like having a perfect map of a territory, but being unable to say what the territory actually is, whether it's land or sea, mountains or valleys, something or nothing. Part of the difficulty is that measurement in quantum mechanics isn't passive observation. It's an interaction between the measured system and the measuring device. The system and device become entangled, their states intertwined. In a sense, there's no clean separation between observer and observed. They form a unified quantum system, but we experience ourselves as separate from what we observe. We perceive definite outcomes, not superpositions. How the unified quantum description connects to our subjective experience of measurement remains profoundly mysterious. Some physicists argue we should just shut up and calculate. Use the theory's predictive power without worrying about interpretation. This pragmatic approach works well for doing physics, but it leaves fundamental questions about reality unanswered. Other physicists believe the measurement problem points toward missing physics, new phenomena at the quantum classical boundary that we haven't discovered yet. Still others think the problem is philosophical rather than physical, rooted in confused questions about the nature of observation and reality. What's clear is that the measurement problem forces us to confront our assumptions about the nature of reality. Is reality objective and independent of observation? Or does observation participate in creating reality? Are properties of objects real before we measure them, or do measurements bring properties into existence? Is the universe fundamentally deterministic or irreducibly random? Quantum mechanics doesn't answer these questions. It forces us to ask them more precisely than ever before. The measurement problem stands as a monument to the limits of human understanding. We've built a theory that predicts nature's behavior with breathtaking accuracy, yet we can't fully comprehend what the theory is describing. It's humbling, it's fascinating, and it's a reminder that reality is under no obligation to make intuitive sense to minds evolved to hunt prey and gather berries on the African savanna. The quantum vacuum, that seething emptiness full of virtual particles, suggests that nothingness is relative, that even absence is a kind of presence. When you feel empty, when life feels void of meaning or purpose, remember that the vacuum isn't truly empty. It's full of potential, of fluctuations, of possibilities waiting to crystallize into actuality. Rest isn't absence. Stillness contains motion at scales too small to see. Even in darkness, even in silence, the universe is doing something, maintaining itself through invisible activity that occasionally bubbles up into observable consequences. Decoherence explains why quantum weirdness doesn't intrude into everyday life. The environment constantly collapses superpositions, averaging out quantum fluctuations into classical definiteness. You can't walk through walls or exist in multiple places simultaneously because you're too large, too warm, too entangled with your surroundings. There's a kind of peace in this. The quantum realm is fascinating, but you don't have to navigate its full strangeness. Your classical experience is real, stable, reliable, an emergent property of quantum mechanics itself, not something imposed from outside. The solid ground beneath you is solid because decoherence makes it so. Quantum mechanics stripped away old certainties but offered new perspectives. Reality is probabilistic, non-local, participatory, and stranger than anyone imagined. But it's also mathematically beautiful, experimentally confirmed, and intellectually coherent. The universe doesn't owe us intuitive explanations. It operates on principles discovered through careful observation and brilliant reasoning, principles that work even when they conflict with everyday experience. There's profound humility in accepting that reality exceeds our intuitive grasp, that we're clever enough to discover these principles, but perhaps not evolved to find them obvious. And now, as your breathing slows and thoughts begin fragmenting into the pre-dream drift, you carry these quantum mysteries with you into sleep. Somewhere, electrons are tunneling through barriers, entangled particles are coordinating across cosmic distances, virtual particles are flickering in and out of existence, wave functions are collapsing, or branching, or never collapsing at all, depending on which interpretation you prefer. The quantum realm continues its probabilistic dance, utterly indifferent to whether you understand it, appreciate it, or even believe in it. The universe doesn't ask for your approval. It simply is in all its strange quantum glory. And you, improbable arrangement of particles held together by forces and fields, maintained by quantum effect keeping your atoms from collapsing, are part of that strangeness. A conscious pattern emerged from quantum chaos, pondering its own foundations as sleep approaches. Let your mind release these ideas now. They'll settle like sediment, finding places in your understanding while you rest. The quantum world will still be there tomorrow, still weird, still wonderful, still fundamentally mysterious despite everything we've learned. But for now, let the questions dissolve. Let the uncertainty principle apply to your thoughts. Position yourself comfortably in this moment, and let your mental momentum drift towards stillness. The wave function of your consciousness is collapsing gently towards sleep, exploring that twilight superposition between waking and dreams. Quantum mechanics reveals a universe more beautiful and strange than our ancestors imagined, a cosmos of possibilities and probabilities where reality emerges from mathematics and measurement. But beneath all the weirdness, beneath the equations and experiments and philosophical puzzles, there's something almost comforting. The universe follows rules. Those rules are comprehensible, even when counterintuitive, and we, against all odds, have managed to glimpse them. So rest now. Let the quantum foam of your thoughts settle into peaceful darkness. Somewhere, in another branch of the many worlds multiverse, another version of you is just waking up. But here, now, in this branch, in this moment, sleep is calling. The particles that compose you will continue their quantum dance while you dream, maintaining the delicate balance between structure and chaos that makes consciousness possible. The quantum realm will be waiting when you wake, strange, beautiful, and fundamentally real. But for now, let it all go. Drift into that space where probabilities collapse into the single certain outcome of sleep. Sweet dreams, quantum explorer. May your wave function evolve peacefully through the night.